Let's get this party started. So we're talking about generalized least squares. This is going to be a very, very basic introduction to it. It's quite a complex topic, so I wouldn't recommend using this video to get a greater insight. This is just for a basic overview to give you some sort of understanding of when it could be used and when maybe you shouldn't be using it. So the definition, Wikipedia. This is what I got from Wikipedia. It's funny because Wikipedia was always looked down upon, but now it's actually one of the most credible sources of truth. I think, at least for data science. I say that before they start changing. I don't know, the crazy shiz. But anyways, carrying on, what it says is in statistics, generalized least squares, or brackets GLS, is a technique for estimating the unknown parameters in a linear regression model when there is a certain degree of correlation between the residuals in a regression model. In these cases, ordinary least squares and weighted least squares can statistically be inefficient or give misleading inferences. GLS was first described by Alexander in 1934. I think I said that really weirdly. But essentially, what it says is estimated for the unknown parameters in a linear regression model. That's saying we could estimate beta 0 and beta 1 with more of an emphasis on beta 1 because this is the coefficient for our independent variables or regressors or explanatory variables, however you like to name it. When there's a certain degree of correlation between the residuals in a regression model. So if this error term is correlated with the previous dependent variable. So this is one prediction. Imagine was doing another prediction. If this error term was correlated with the next prediction, then we would be using some sort of GLS. Often that comes up in the form of a Riemann model or some sort of time series model that you'd use to incorporate that correlation between the residuals. But also, it doesn't mention it here explicitly, but this includes as well as homoscedasticity. So if your variance is changing depending on the value, the observed value, then that is violating homoscedasticity, and therefore we call that heteroscedasticity. But I'll go into more detail about that soon enough. But just before we go on to that, I'm just going to quickly do a quick interlude of the Gauss-Markov assumptions. So the 5 Gauss-Markov assumptions are, I'm not going to say them, but essentially the one that we could see, spoiler alert, OLS 5 at the bottom is being violated. There is homoscedasticity and no autocorrelation in the residuals. So if any of these assumptions are violated, this will mean that the model that we use, or ordinary least squares, will no longer be the most efficient. It won't be BLUE, which is an abbreviation for the best linear unbiased estimator. So if it's no longer BLUE or no longer the best linear unbiased estimator, OLS is not the best. So now we have something better, which is GLS. So this is GLS now. It's going to help us with violating that 5th assumption at the bottom. This will basically mean that GLS is now the best linear unbiased estimator. So this comes up in the form of you'd use generalized least squares or GLS or not JLS, either for heteroscedasticity. So that, like I said before, is when your observed values, like in a graph that you can see next to it, if the variance changes depending on the value of your regressor, then that means that your variance is not constant. It's varying, obviously. So you have varying variance. Haha, it's quite funny. And therefore, violating homoscedasticity, which is the 5th assumption over there, and correlation between errors, which was previously mentioned. But what I find interesting is that you would not use generalized least squares for normality of errors not being held. So if there is a model that you have and you find out that the errors are not normally distributed, that is not an indication of you should be using generalized least squares. Because if we go back on the Gauss-Markov assumptions, pause the video, have a look at it, none of them mention anything to do with normality of errors. normality of errors and breaking that assumption will lead to some issues with using ordinary least squares in terms of particularly understanding the p-values and creating your confidence intervals for your coefficients, but this is no longer a concern of the Gauss-Markov assumptions, and OLS will still be the number one best linear unbiased estimator. So, in short, normality of errors, if that's violated, that's not Gauss-Markov or OLS's problem. You have to still run with it. Check my other video. I talk about homoscedasticity, normality of errors and what to do in the case of this being violated. But OLS is still the best estimator for this. It's just that the interpretations you make from your p-values and confidence intervals will no longer be completely valid. So this is the fun part. How is it actually done? And I hope you're prepared. This is going to be quite a roller coaster, but if you pay attention, I think there's a potential that you could understand what I'm about to say. It's magic. That's essentially what GLS is. It's magic. And I can't really be bothered to talk about magic in a great detail because I don't really understand magic that well. But to just give you a brief overview of that magic, there's two main things that people use for generalized least squares, and this is weighted least squares and also feasible generalized least squares. These two methods, from my understanding, is essentially weighting the original equation by the standard deviations of the observed values. So that means that you're dealing with the problem of it not being homoscedastic by basically weighting the original equation by those variances that the observed values have. And once you've done this weighting, then you apply ordinary least squares. And that's essentially what generalized least squares is doing. And I do not really think it's worth really going through the maths for it, because it is quite difficult for someone who hasn't been doing a maths undergrad. So I think, I'm just going to leave it at that point. Feel free to check Wikipedia. There's some great links if you'd like to understand more, but this is just a high level overview. I hope you enjoyed, and Godspeed.